So hello and welcome student for today's lectures. So let us begin today's lecture MA415 Algebra, and this is lecture number 32. Okay, now recall in our last lectures we discussed about this important idea of Gauss lemma. Okay, so Gauss lemma tells you about the factorization of relationship between factorization of a polynomial on a over a unique factorization domain and its field of fractions, right? The relation, and then we prove the corollary that if you start with a polynomial which is primitive, then it's irreducible if and only if irreducible inside that field of fractions, right? So this thing we already proved, and today we are going to use this idea to prove one of the main important theorems which we were planning in last lectures. Okay, so what was the idea? That if you start with a field, if you go to the polynomial ring over that field, if you start with any domain, then what is the minimum property you require so that the polynomial ring over the domain preserve the property, right? And this is actually called the unique factorization domain, UFD property. So what is the theorem? Let R be an integral domain then R is a unique factorization domain, unique factorization domain if and only if what happened if and only if Rx is also unique factorization domain. So Rx is what? The polynomial ring over R. Okay, Rx is also also means is also unique factorization domain. Okay, so this is one of the very much important property that unique factorization domain possesses. Now you recall that this property is not true for other domain. For example, PID. If R is a PID, then Rx is not a PID always. Okay. Similarly, if R is a ED or R is a field, that polynomial ring may not be the same property, right? But UFD has this nice property. Okay, so how do you prove this kind of statement? So proof. So you can see one part is obvious, like so let me write down the obvious first part. So let Rx be a unique factorization domain, unique factorization domain. Then what happens if is in factorization domain? Then what happens? Then every element for any. So I need to prove that R is unique factorization domain, right? So then for any R belongs to R. So are also an element of Rx, right? because Rx contains capital R. Okay, so for any R this thus the UFD property of Rx implies small r can be factors factored uniquely as a product of irreducible in R. So in Rx. Okay. So now note that R is an element of R, capital R. So if you in the factor of this, so that is what that is. You can write down R equal to R1, R2, something Rn, where these Ri's are irreducible in Rx. Now note that these are constant polynomial, right? So they has to be inside also R. So this polynomial has to be inside also R, right? So that is this R is also obviously I'm not taking units, so I should say for any okay. So R non-zero non-unit. If it is non-zero non-unit, zero unit, there is nothing to prove, right? So I'm assuming non-zero unit, then only you can do this thing, right? So so what you can do, so yeah, so also R can be also this uniquely factorial also factors in capital R. Okay, so every element of capital R can be uniquely factors into product of irreducibles. Okay, so so this is a simple observation, and that gives you the proof that capital R is a UFD, right? So that means UFD, because if I can do the converse part also proof. So no, you can prove this thing in different way also. You can assume that suppose R is not a UFD, then also you can show that capital R is not a UFD. Okay, clear. So now conversely let capital R is a UFD, unique factorization domain. Okay, and I need to prove that capital Rx is a unique factorization domain, right? So what I'm so let you start with a non-zero non-constant polynomial. Okay, so if it is constant polynomial, you don't have any, I mean, this is obvious, constant polynomials are element of R, so it's okay, right? So what you do is you choose a non-zero non-constant polynomial in Rx. Okay, and you choose the field of fraction and let A be the field of fractions of R. Okay, so what does that mean? That means you are thinking this px is also element of fx. So now as fx is UFD. Fx is always UFD, right? Whenever you have field, and then you know that polynomial ring over the field is always a Euclidean domain, and hence it is a pseudo-ideal domain, and hence it is a unique factorization domain, right? So Px can be, so Px can be factors into product of irreducible product of irreducible. Okay. So one thing you can assume here, I can assume that P is so without loss of generality, without loss of any generality, we may assume that Px is a primitive polynomial. Okay, so you remember the meaning of primitive, whose content is 1, primitive polynomial. Okay, why I am saying without loss of generality? As otherwise what you can do, otherwise we will write down, we can write this Px equal to that content of P into some P dash x, okay, where P dash x is a primitive polynomial, right? Because content means the greatest common divisor of the coefficient. If you can take out, that becomes a primitive polynomial. Okay, so you can always assume that this is Px is a primitive, otherwise you can write down that thing, and the Cp is element of R, which is a UFD, right? So what you can do, you can write down Cp also in terms of some P1, P2, something, Pk, whatever. You can write down in factorizations. Okay, so there is no problem. You can assume that your given polynomial is a primitive polynomial, right? So now let us assume that let Px be a monic. Px, see, I'm not saying monic. Monic means leading coefficient is 1, but I'm saying it's a primitive polynomial. Okay. See, monic polynomials are always primitive, but primitive polynomials may not be monic. Okay. So primitive polynomial in fx, right? As fx is a UFD, so what you can write down? You write down your Px in terms of product of irreducible something, P1x, P2x, and something, say Pnx. Let me write down that. Write this in terms of irreducible in fx. Okay, so you're writing this product of irreducible in fx, and then you just recall that what Gauss lemma said. Gauss lemma says that once if you write down something product of something inside that field of action, then there will be always a factorization inside. Or maybe let me write down, this is P dash this. Okay, thus Gauss lemma implies um, the existence of factors in Rx also, right? Because whenever you have a factor in irreducible inside fx, then this one fx, and that is you can write down your px equal to, now you can write down, let me write down p1x, p2x, and some pnx, right? And where, so not only that, where these are actually this f multiple of this p I dash x are f multiple of multiples, or rather I should say yeah, whatever, both sides multiples of pix. Okay, so this is coming from Gauss lemma. Okay, so what do we had? We have a product. You can write down px in terms of product of polynomials into this Rx, right? But how do you know this is irreducible? That is the question. This is irreducible inside fx, but how do you know this is irreducible inside Rx? Again, that is the corollary of Gauss lemma. What that said? That said that if you have some polynomial which is irreducible inside fx and they are primitive, then this is also irreducible inside Rx, right? Now can you say these are p1, p2, pn are primitive? And this is obvious. Why? Now as if px is a primitive polynomial, all the pix are also primitive polynomial, right? Primitive polynomial. Clear? So if we have product of primitive polynomials, and so what does that mean? That means that is thus using the corollary of Gauss lemma, that we proved last lectures. What do we have? We have all the pix are irreducible in Rx. Okay. So done. So we have a product of irreducible in Rx. Right? Does this prove our theorem that Rx is a UFD? No, actually, because the uniqueness property I did not prove it. Okay. Now we prove the uniqueness property, right? Uniqueness property. So property. So what we can do? So let us assume that you can write down px in terms of this that p dash in x and some q dash 1, q dash 2, and q dash some s of x in capital Fx, right? You can write down this because capital F is UFD. So as capital F is USD, so you can easily see the n equal to s as they have the same number of factor, right? Because S is UFD, so in UFD they have this only one factorization, right? Up to unique, up to associates, and not only that. See. Maybe I can write down Rx also, no problem, because this is if I choose an Rx, then also they are in fx also, and fx is UFD, so they are same. Okay, so let us choose an Rx only, the factor. Maybe I don't need then bar here. Okay, let me choose an Rx, sorry, dash, yes, and don't put this dash. Okay, so an Rx is obviously sitting inside fx. So this p1, p2, pn, and this factorization will be unique. So there has to be is equal to n. Okay. Now what do you know? We know that whenever you have two such factorization in fx, then they will be kind of associates in f, right? So this is pi. So let me assume that pi's and qi's are associates. So I am assuming that after some rearrangement, p1 and p2, py and qi are associates. Okay. So you may say that why it may be p1 may be associated to q3, right? And no problem. Then I will write down q3 equal to my q1. Okay. So associate in fx. We can write what we can write. You can write that say pi of. So let me write down you just p1. Say only. Let me do it for each I. Say p1. Okay. So what you can do that your p1 is it is true for everything. So something say a over b and q1 of x. Okay, so where this is belongs to a with I'm taking the smallest factors, so smaller representation, this is 1. Okay, the GCD will be equal to 1. So thus we have what we have from this. We have that b times p1 of x equal to a times q1 of x. So there is no, see, this 1 is not important thing, because this is true for any q2, q3, qn. So if you can understand for 1, you can understand for everything, right? Okay, so yeah, so this b p1 of x will be equal to a q1 of x, and then you find out what is the content from this polynomial. Now you see the content of b p1 of x equal to b as p1x is primitive. Okay, similarly this content of a q1 what was that a q1 of x is a as same thing, this q1x is primitive. Okay, so what does that mean? That means see, they have different content, right? So the content of this has to be equal to content of this, right? But the GCD of a and b equal to 1. So what does that mean? So this means that they have to be yeah, maybe I don't want to write down. Okay, should I say GCD? Do I need a GCD thing? That's all. Let me think about it. No, GCD is not possible actually. That will leads to the fact that see, a divides, you cannot divide b, right? So a divides, this is impossible. So yeah, so this is I don't require GCD here. It's just a multiple Okay, and this will force me what? This will force me that yeah, so this content and this, and then this is equal to this. So what does that mean? That means this, see, A cannot divide P1x, right? Because this content of P1 is 1. Similarly, B cannot divide this. So what is the only factor comes? That A and B must be associated to each other. This is the only thing that comes. Okay, so thus you can say that A equal to some unit times B for some unit U. Okay, so thus what does that mean? That you can write down your P1 of x equal to U times. So if we replace A equal to UB, so B get cancelled, so U times Q1 of x, right? And this is true for every I. So this is true for all PIs. Okay, so for all PIs, these are some unit time multiple of QJs. Okay, so what does that mean? That means this factorization of Rx, Px in terms of P1, P2 and Q1, Q2, if I write down that thing, then they are nothing but the associates. So that means unique, right? So this completes the proof. I am not writing anything else. Okay, so this is the proof of uniqueness. Okay, so what you can say from this theorem, so the important thing you can say from here is that you can say corollary, that if you start with R and then you know that Rx, so R UFD implies Rx1. So for example, for one variable is UFD, and that implies in two variable also Rx1 x2, right, which is nothing but polynomial ring of x2 over x1 Rx1, and similarly so on Rx1 x2 xn. If you choose any final many things, they are all UFDs, right? They are all UFDs, right? So you can attach, it doesn't matter how many finally many variable on a UFD, and their polynomial ring will become again a UFD. So this is one important very important property of UFD. Okay, now as we are talking about irreducibility, so one can ask a very important question: how do I check? How do I check something is irreducible or not for some ring? Okay, so that thing let me discuss. You can say that this is irreducibility criteria. Irreducibility criteria. Okay, so let us first think about over Q what happened, and then we will discuss for general ring. Okay, so for example for integral domain, because otherwise it's a minimum integral property is required for us to prove many theorems. Okay, so if we start with a polynomial, same a0 plus a1x plus dot say a n minus 1 of x to the n minus 1 and x to the power n. So I'm just writing monic polynomial in qx over q, polynomial over q, and let us see what is happening here. Because I am taking monic polynomial, otherwise I can divide, because leading term is non-zero, so I can divide it by the thing, and again I am getting in the polynomial inside qs, right? So in this, what is the criteria to irreducible and reducible things? For example, so reducible means if I find the root of this polynomial, then I can say that this is reducible, right? So if if you have something, say p by q, so it belongs to q. Here let me assume that GCD is 1, the smallest such factors is a root of px. Then क्या होगा? Then this p of p by q is 0, right? This is a root. So what does that mean? That means that you can plug this thing and then you can have a0, a1, p by q, and then similarly a2, p square by q square, and so on, and then an minus 1, p to the n minus 1, q to the n minus 1, and last one is p to the n, q to n, that is equal to 0, right? And then multiplying both sides by q power n, multiplying both side by q power n, we get what we get. So we get that a0 into q power n plus a1 into p into q power n minus 1, and so on, and then a n minus 1 into p to the power n minus 1 into q, and the last one is nothing but p to the power n, that is equal to 0, right? So this becomes 0, and okay. Do I need a monic polynomial? Yeah, I think I can easy. Without monicness also you can prove it. So I'm thinking. Yeah, so let us prove it for general polynomial first, then monic polynomial case will come directly. Okay, so for general polynomial, what happen? You can have a n x power n, right? Yes. So in general, if you have a n here, then a n here, right? Yes. So now so I am assuming that p and q are GCD1. So what does that mean? That means so two things is possible. So one thing is that you write down a0 q power n one side and take everything other side. If you take everything other side, you see that p is common in every term. So you can write down that p times whatever the remaining term, right? Remaining term is a1 q to the power a1 q to the power n minus 1, and so on. And last term is nothing but yeah, so an q power p power n minus 1, right? So what does that mean? So this implies p divides a0 as p does not divide q, right? Okay, so this is one criteria that you should get. If something is a root, then the numerator must divide the constant term. Okay, and again you can write down this thing in another way also. You can write down this part, you can take outside. Again you can write down this n p power n, and then you can minus of q times all the other factor, right? So what does that mean? a0 q power n minus 1, and so on, n minus 1 into p power n minus 1, right? And you see again, so this implies q divides n as q also does not divide p. I mean the GCD is okay, I should not say this. I should say GCD is p and q is 1. Similarly here also I should say same thing. GCD is GCD of pq equal to 1. So there is no common factor. So that means this. So what does that mean? The denominators must divide the leading coefficient, right? If something is in reducible. So what you can write down? So conclusion you can write down that let px is equal to a general polynomial in x power n in qx, then any p by q with this GCD p by q equal to 1 is a root of it's a root of and then if any the root of px, then what happened? Then p divides the constant term and q divides the leading coefficient n, right? Okay, so what does that mean? That means if we start with a monic polynomial, then what happened? Now in particular, in what that I was telling, in particular, if n equal to 1, so you don't have to prove anything, right? If n equal to 1, because then I mean q has to be plus minus 1, there is no other choice, right? So this is kind of integer, right? So what you can say, in particular q equal to 1, then if this p of the factors write down, so d not equal to 0 for all d divides a 0 implies if p is irreducible, right? Because if it has a root has to be a integer, because q has to be plus minus 1, there is no problem, and that root must divide a 0. So if it is not 0, so what does that mean? That means for all the divisors of a 0, you have to check only that part. There is nothing else you need to check. Okay, so you check whether the divisor of a 0 p of that is 0 or not. If it is not equal to 0, then this has a irreducible polynomial. So maybe I will give an example. So example, so maybe, so let me just write down, say x3 minus 4x okay, 2 into 2x plus 2. Say what will write down this polynomial. Okay, this is my polynomial, this is my fx, px, whatever. I want to know whether it has it is reducible in z or not, and as you see that as px is primitive, it is enough to prove that px is irreducible in qx. Okay, so if it is irreducible in q, then it is also irreducible in z, right? That is coming from Gauss lemma, that corollary of Gauss lemma. Okay, so over q, what do you know? So over q, if this is a harmonic polynomial, right? Leading coefficient is 1. So we need to check that so as px is a monic. See, monic means what? So let me tell you, monic means n equal to 1. Yeah, so where is that? Yeah, so this means monic polynomial. As this is a monic polynomial, that is that a in the leading coefficient is 1. Okay, so monic polynomial means what? Monic polynomial means that the roots must be integer, right? If there is a root, and the divisor of the constant. What is the constant term? constant term means plus 1, right? Constant r what plus minus 1, right? So let me check whether for plus minus 1 it is 0 or not. We need to check the p of plus minus 1 equal to 0 or not. If it is reducible, it has to be 0. If it is irreducible, then it cannot be 0. Now we see that p of 1, what is p of 1? P of 1 equal to 1. Here you are getting 1, here you are getting minus 4, here you are getting 1. So what is that? So 1, 1, 2, minus 4, minus 2. And p of minus 1 equal to what? So this is minus 1 and then plus 4. So minus 1 minus plus 1 0 plus 4. So this is plus 4, right? So thus px is irreducible over ring of integer z. Okay, so these kind of problems are important problem. You can get this kind of problem. Okay, so this is for criteria for Q. Now if you want to find out the criteria for general integral domain, okay, then what you can do, and this is called the Eisenstein criteria. It's very, very important. Okay, so let me discuss it here. Eisenstein criteria. Okay, what is Eisenstein criteria tells you? So I will first do it for general ring and then for the ring of integers, which is important, but that will be just a corollary from the general ring. So what is the property of general ring? So let R be and integral domain and P be a prime ideal of R. Okay, let you have choose a polynomial, say what about the px? Maybe I am writing too many p, so let me write down f. Otherwise you have an ideal p also, so fx equal to, you write down so I am taking a monic polynomial here, so a0 a1 a0 a1 x plus, okay, a0 a1 and then say n minus x by n minus 1 and sorry n minus 1 sorry, no, I don't need n. So I am just taking monic polynomial, so x power n. So what happens if you have a such kind of monic polynomial in Rx? Okay. Now if this a0 a1 and a n minus 1, all of them, whatever you choose, so they belongs to P, but a0 does not belong to P square, the ideal general. P square means the product of ideal P, right? Then this fx is irreducible. Okay, is irreducible in Rx. Okay, so you understood. So so if you find out this polynomial such that all the coefficients are inside that prime ideal, but the constant term is not inside that square of the prime ideal, then it is irreducible. Yeah, so how to prove this kind of statement? So you can prove that contrary, right? So on the contrary, let us assume that this is reducible, right? So you can write down fx equal to something, say px again p of f1x f2x, okay, in Rx. Suppose you can write down this So what you can do, Rx with this f1 and f2 non-constant. In this constant there is nothing to write, right? Non-constant. Okay. Now what will be the image of this polynomial inside R mod P? Okay, so then you write down f bar x equal to f1 bar x, f2 bar x in R mod P over x, right? But the moment you go R mod P, what you have? You see that a0, a1, an minus 1, that all vanishes, right? So what does that mean? That means f1 bar will become x power n, and that will be f1x bar, f2x bar. Okay, that will be inside R mod P, this, right? But R mod P is an integral domain, right? So obviously, and this is a prime ideal, because P is a prime ideal, is integral domain, right? So see, so what does that mean? That factors don't have any constant term, right? So that means f bar x, and they have zero constant term. The constant term must be zero constant term, right? Because at least one have a non-zero constant term, and this is the integral domain. So 1 minute. Yeah, so there is no constant term in this side, right? So if okay, so one what you can say, 1 minute. So this is integral domain. So what you can say, so this is the constant term is 0. So if they have a constant term there, and that constant term is not inside P, right? And hence yes. So if they have a constant term which is non-zero, so the constant term, if you take the product, that will be the constant, that will be inside the constant term of f, right? But constant term will be inside P, right? So P is a prime ideal, right? So this is the important observation, that the prime ideal property will gives you that this has no constant term. Okay, so once they don't have a constant term, what you can say? You can say that the original factor f1 fx has constant, their constant must be element of P actually. That's why when you go modulo R mod P, that becomes 0, right? So thus the constant term of f1 and f2 are the element of P, right? The ideal P. But if you take the product of these two constant term, that will become the constant term of P. So thus the constant is 0. Is the constant term of P is the product of the constant terms of f1 and f2, and so a0 belongs to P square, right? Because the constant term of f1 is element of P, constant term of f2 is element of P, so the product has to be element of P square. But this is a contradiction, which is a contradiction. So what does that mean? So remember, we assume that a0 cannot be element of P square, right? But here we prove that it is element of P square. So what does that mean? That means your fx is irreducible in Rx. Clear? So to check something irreducible Rx or not, you just have to check whether all the elements are inside a prime ideal. Find out the prime ideal. Okay, so that prime ideal you need to find out. but the constant term is not inside the product of the prime ideals. Okay, and the immediate corollary of this thing, which we generally call also Eisenstein Criterion, but this is for integers. Okay, Eisenstein Criterion. Okay, so what you can do, so you write down your fx, this element a0 plus a1x plus an minus 1x plus x power n minus 1 x power n, this is element of zx. Okay, and let p be a prime in z such that your p divides ai for all i equal to 0, 1, 2, n minus 1, but p square does not divide a0. Okay, so that means a0 does not belong to the ideal of generated by p square, right? Then if this is the condition, then fx is irreducible over z, so it is inside zx, right? Okay, so so maybe some examples. So let me give you some examples. So you choose your fx equal to something, say x power 10 plus 4 x power 6 plus 10 x square plus what is this? Write down. It doesn't matter. You write down something plus 2. Okay. Now you see that 2 divides all the coefficients, right? 4, 10, 6, 2. But 2 square does not divide constant term 2. Okay, so this fx is irreducible over zx. Okay, so you can easily find out lots of such examples, and there might be some kind of problem in exam also. Okay, so with that I am going to stop today's lectures.